Hello, I'm going to describe POSH, NOSH TDTR for metrology of materials, devices, and packages. These are new products based on picosecond and nanosecond optical sampling for heat transfer analysis. The principle of this technique is used to solve thermal characterization challenges both at the material and device level as well as in packages. In the case of materials, we have quite a bit of different materials with different thermal properties. In addition, we need heat spreading layers such as diamond silicon carbide. We have different materials, but also the heat transport happens at the time scales from gigahertz to DC. In the case of packages, typically we work with bigger structure, but the challenges are 3D chips, copper vias, as well as hybrid binding interfaces. In order to do thermal characterization, we need to cover about a factor of 1,000,000 in length scale from tens of nanometer in the thinnest material to centimeters in the packages, and a factor of million, 10 to the 12 to go from picoseconds, which is really heat transport at the smallest layer, to seconds that happens inside packages. And all of this will allow us to study 3D properties of devices and packages. What we have done is that we have combined pump probe thermoreflectance, both single point and full field imaging. The Microsanj has had this lock-in imaging for quite a few years. We have added a pump laser that creates heating, and by doing this, we can now do material and package characterization. Another innovation is our expertise in precision timing and synchronization used in lock-in imaging. We are using a dual laser synchronization with a wide transient dynamic range, which is quite unique. We can go from hundreds of femtoseconds to microsecond, even DC, and do both single point as well as image. And the real principle of this optical sampling is when you have two lasers with closely related repetition rate, we are able to do down conversion and obtain transient signals quite accurately. Here is example of a system where a standard probe station, the optical head is modified to be able to do transient imaging, thermoreflectance, as well as pump probe lasers that send the signal. But also this could be a breadboard optical kind of a setup for material characterization if one does not need a probe station. Data acquisition is quite straightforward. One can obtain transient profiles over times of hundreds of picoseconds to microseconds to even millisecond and study how the surface reflection changes. Here in this case, pump and probe, you can be visualizing and study heating near a pump or at the pump. But also you can do the full imaging of the field because we have the camera. Another key component is parameter identification software. The heat transport in the rails is complex, it's 3D. There are various parameters can affect the shape of the transient. It could be what type of transducer is used, what film properties, what interface thicknesses, and what substrate properties we have, what are the laser characteristics. But at the end, using 3D analytic technique, we are able to fit within a few percent, and this is used to study what is inside the material. So take-home message is that we have a pump probe thermal characterization that can cover a time range of picosecond to DC. Optical spatial resolution, because we use various visual wavelength, can go down to quarter of a micron. And cross-plane spatial resolution, heat transport goes from tens of nanometers to hundreds of micron, of course, depending of the material's thermal properties. This can be used to study materials with thermoconductivity with wide range, thermal boundary conductances in a wide range, and 3D ICs and multi-layer structures. Please contact us if you have any questions or comments. Thank you.